Here's part 4 of the series on interval questions involving kinematic equations. This type of problem are called chase-catch problems, where we actually have two different objects doing two different things that we're trying to figure out like when they're gonna kind of catch each other. So here, for example, we've got like a Honda and a Ford driving down the highway, and the Honda's traveling faster than the Ford, and we're trying to figure out, well, like how long will it take for the Honda to catch up, or how much distance will they have traveled by the time the Honda actually passes the Ford? Well, this type of thing we look at here. So we're going to actually draw two separate diagrams here beside each other, and one's going to be for the Honda, one's going to be for the Ford. This is the way I like doing it. Kind of helps me understand what's going on. So the Honda is starting at point A, and it's going to be moving at a constant velocity, and it's going to keep moving until at the end we're trying to figure out like how far it's going to travel by the time it reaches the Ford. So it'll be at some point over here. Now this Ford is starting a little bit ahead. So if you look at the Ford, it's got actually, if you see here, we can see the Ford has a 58 meter head start. The Ford is 58 meters ahead. So we actually have 58 meters here before, at the very start, where let's call this A prime. So this is A prime is just kind of differentiating point A for each of them. This is where the Ford starts. You could also call this B. So they both end up at this point B. Okay, so let's just write down how fast they're moving. So this Honda is moving at the Honda, let's call it VH, is 115 kilometers per hour, and we got this V Ford is going to be traveling at 102 kilometers per hour. Now, let me grab these and move them, because I'd actually like to do a unit conversion here and change it into meters and seconds, because it's not going to take hours for the Honda to catch up and stuff. It's probably better to illustrate this in seconds. So it's always good practice typically to put in meters per seconds. We probably could still do this one with kilometers per hour, but just a safe practice, you always want the units to be the same. And I often use meters per second. And actually, in this case, we actually have this in meters, so we definitely need to change things all to the same. And I think it's best just put everything in meters in this situation. So let me just do this conversion in a fast way. We can literally multiply. All I'm going to do is multiply this number by 3.6. That's my little trick to get the. Oh, sorry, in this case I'm dividing by 3.6 because I'm going into meters per second. So I'm going to divide this value by 3.6, divide this value by 3.6, and that's going to give me meters per second. If you want meters per second to kilometers per hour, you just multiply by 3.6. And that just comes from the changing kilometers to meters and hours to seconds. So dividing 115 by 3.6 gives me 31, oops, let's change that color, 31.9, we'll leave it as 94 meters per second. And then we've got for the Ford, dividing that by 3.6, we get 28.33. Okay. So what I'm going to do here, and we're going to do with any of these types of problems, right? You're going to want to use equations that have time in them and displacement in them. Because displacement is a thing that is going to be the same at some point. Like when this this first vehicle goes from A to B, it travels some displacement. And then if we really start from like this head start plus the amount the Ford travels, that's going to be the displacement of the Ford. And it turns out that these, like if you look at this, these lines are the same length. So displacement is our, like we could say the displacements are equal when we kind of set up like this. And then also the other thing that glues these situations together is time. They're going to be moving for the same amount of time. So the fact that we can set the variables with these similarities allows us, even if they're doing different motion, it allows us to connect them and solve for things. So in this case, what I'm really going to connect here, I'm trying to figure out like this displacement from A to B. So so for D, my displacement for the Honda and this kind of displacement for the Ford, right? We need them to be equal when they reach each other. That's what we're trying to figure out. So this Honda has an equation. It's a constant velocity equation. So we can just use this one, right? V equals distance over time. And we can just rearrange that for distance. So we're just solving that, and it's just Vt. So I just have Vh time, right? And then my equation for displacement for the Ford is going to be, now this is a little trick, it has that 58 meter head start plus like the displacement as it actually drives, right? So we got V of the Ford times time. Okay, so this is the trick. For these lengths, as I was showing, for this length to be equivalent to this length, I need to go 58 plus the distance as the Ford drives on the highway. So now that these equations are equal, we can now substitute. We also know the actual rate at which they're moving, so we know 31.94 time, and the 58 plus 28.33 times the time. So now it's just a matter of solving for time, and once we know time, we can then substitute back and get the displacement. So bring this other. Sorry, let me fix this. We're going to bring the 28 to this side. And that will be, so that's 31.94 minus the 28.33. That's going to give us 3.61 times time, and then divide that on both sides. So we're going to go 58 divided by 3.61, and we get a time of 16 seconds. Okay, so we now know the time. The one question is how much time it'll take the Honda to catch up. It'll take 16 seconds. And then we also will look at how far they would have traveled. So the one car, so the Honda will have traveled a distance of, let's see here, the Honda of our time is going to be 115. Oh, not 115, sorry, let's just use the meters per second. Because our time is in seconds, 16.07 seconds. And we got our distance for that. So we get 31. So we get about 48 meters here. That's how far that Honda is going to travel. and then we'll do it for the Ford. Now the Ford is going to just have moved VF times our time. So it will have traveled for 16 seconds. And notice how we don't include the 58 meters, right? We just kind of neglect this because that was already there. But we want to know kind of like how far it traveled from here to here. So we just use it's traveled for 16 seconds. And it was moving at 28.33 meters per second. And that gives us a distance of, I think I might have messed up my calculation here for the first one too. Let me just do that again. 31.94 plus 16.07. Yeah, it is 48. Doesn't make sense actually. Okay, that's better. Made this equation that's wrong twice. Okay, so looking at the distances these two vehicles traveled, we're going to use our equation as you can see here. We put in our velocity that we're traveling in meters per second. We put in our time of 16.07 seconds that we found. And we find when we put this in the calculator, we get 16.07, 500. This is going to be done over 513.27 meters. And for the Ford, it's going to travel 455.26 meters. Notice that I didn't include this 58 meters for the Ford. We're really looking for just how far to travel during this time interval, so it moved that far. It required the Honda had to travel even further, right? It had to travel that 58 meters plus a little bit more, and then that total distance it traveled was 513.27. So this is the process you'll use for any type of problem. You could have one object accelerating, one object not. The only thing that would change is this equation would now be an acceleration type problem, and you just choose one of those equations that have both displacement and time in them. And likewise for this, say like this other car was accelerating, you would just change this piece only and choose one of those equations. Like I said, will have the displacement and time in it and set up like that. Hope this helps. Good luck.